A confidence interval for a proportion is a confidence interval for the parameter p in a binomial distribution. For example, consider planting a sample of 100 seeds, counting the number of seeds that germinate, and using the result of that experiment to estimate the germination rate p of the entire population. In this illustration, 70 of the seeds germinated, so the germination rate in the sample, or sample proportion, is 0.7. The sample proportion is conventionally denoted by the symbol p hat, which is p with a caret above the p. The sample proportion is a point estimate for the population parameter p. A formula for the confidence interval can be worked out by treating that sample as one of many possible samples that could have been drawn from the population and considering the distribution of sample proportions calculated for those samples. In this example, that distribution will be a binomial distribution with sample size n equals 100 and unknown population proportion p. It is possible, and quite common actually, to compute a confidence interval using that binomial distribution, but it is easier and probably more common to approximate that distribution with a normal distribution and to compute a confidence interval from that normal distribution. The normal distribution is a very good approximation if the sample size is large enough and the population proportion is not near 0 or 1. If the sample size is small, then the binomial distribution is not well approximated by any continuous distribution, and if the population proportion is near 0 or 1, then the binomial distribution is skewed to the right or to the left and is again not well approximated by a normal distribution. A common guideline is that the normal distribution is a good approximation if n times the sample proportion and n times 1 minus the sample proportion are both greater than or equal to 10. Those conditions are satisfied in this example. With the sampling distribution approximated by a normal distribution, the confidence interval for the population proportion can be computed using the formula from an earlier section for a confidence interval for the mean of a population with known standard deviation, simply replacing the sample mean with the sample proportion and the standard error with the standard error of the binomial distribution. The standard error of a binomial distribution for sample size n and proportion p is given by this formula. The critical value z star for a 95% confidence interval can be computed as before using the inverse CDF function. And with those values entered for the sample proportion, the critical value, and the standard error, the formula for the confidence interval can be evaluated to get the endpoints of the interval. In the hypothesis testing package, there is also a function normal CI that can be used to compute this confidence interval. A confidence interval can also be constructed for a difference of proportions. For example, consider comparing the proportion of seeds that germinate in a sample of 100 seeds with the proportion of seeds that germinate in a second sample of 50 seeds that receive some special treatment, such as some change in growing conditions. Both of these samples are assumed to be samples from large populations. The sample germination rates of 0.7 for the first sample and 0.8 for the second sample are point estimates of the germination rates of the two populations, and the difference between these estimates is a point estimate of the difference between the two population germination rates. A single pair of samples cannot give precise information about the difference between the population proportions. A new pair of samples would, after all, likely give a different estimate for this difference. A confidence interval does, however, show what can be inferred about that difference. The formula for the endpoints of the confidence interval uses the point estimate of the difference plus or minus the margin of error, where the margin of error is the critical value multiplied by the standard error. The standard error to use here is the standard error of the difference of sample proportions, which is well estimated by a combination of the standard errors of the individual sample proportions. The critical value z star is the same as in the previous example, and with those assignments the formula can be evaluated to get the endpoints of the confidence interval. In this example, the 95% confidence interval extends from about -4% to about +24%, so this data gives 95% confidence that the germination rate of the second population is somewhere between 4% worse and 24% better than that of the first population, which is a rather wide range. The next section is about making this range smaller by increasing the sample size.